So part 2 of our course is probably the section of our stats class that you're going to find the most useful when you leave this class, whether we're talking about your job or other classrooms that you're in, because it's all about summarizing and looking at our data. So when we did our little prequel activity this last week, we saw, okay, we can use a graph to look at a relationship between multiple variables. We can use a graph to just see what the distribution of a variable is, and we're going to break that all down a little bit more in part 2. So we start with the simplest situation, displaying or summarizing a single categorical variable. So we only saw one example of this, and that was the first graph where we split up the children from poor families based on their parental education, right? So we had a subset, which was children from poor families, and then we just asked one question, what's the education level of your parents, and displayed that. So when we're talking about a categorical variable, we have something like education level, which is also in this graph. We could also look at gender. There's a lot of different possible categorical variables, right? If we're summarizing a categorical variable, one easy way to do that is to do what we call a frequency table, which is exactly what you see below, right? This just takes our original data set, which would just have everyone listed along with their education attainment, right? And just summarizes it by figuring out the count in each category. So we got our frequencies. In addition to frequencies, you can sometimes see or be given percentages, right? So 2 out of 40, that's 5% of the people in this sample having a high school degree. Just as a quick note, when you have these, either one, whether we're using frequency or percentage in a table, it is nice to give both. The reason is that it's not all of us, when we see 2 out of 40, do we recognize that that's 5%, so it's kind of nice to have that there. And if you give just this row of percents here, you don't know the magnitude of the sample size. Like, is this, if this is 5% of 1,000 people, that's a much bigger deal than here. We see it's only 2 out of 40. Well, one more person would have made a huge difference in that percentage. So you do want to keep numbers as well as percents usually in your frequency tables. Beyond tables and numerics, we can also use displays, and we saw both of these in that activity, bar charts and pie charts. Right, the pie chart we happened to see looked at budget, so it had 2 different variables in there. It had both the categories for the budget and the amount budgeted to them. But generally, we can use them to also display a single categorical variable. One note here: you can't use a pie chart if there's a possibility of choosing more than one option. So you definitely need something that sums up to 100%, so you can divide up that pie evenly. And even with something as simple as a bar chart, we can have issues and we can have things that are misleading. So I have this example as well as a link to a lot more graphs that have lied to us, but from Fox News of Obamacare enrollment. If you dive into this graph a little bit deeper than just cursorily looking at it, you go, okay, from a cursory glance, here's the goal and here's how many people have enrolled, right? You're going, okay. They only have 4 days left, and it looks like they have a long, long way to go, right? They have less than half the people that they have as their goal. But then when you dive a little bit deeper into this graph, you see these numbers are not that different. I mean, it's 1 million people, which is significant, but the way this is written out, it looks like this is over twice as many people that they still need in terms of enrollment. So what's wrong with this graph is that it actually violates something us statisticians call the area principle. And that is when your first cursory look, that first instinct is to look at the area of the 2 bars. And in this case, this bar is less than half of the other bar, which is not what's true about the numbers. So in order to not violate the area principle, what they could have done was not truncate their axes. They could have brought these down to wherever they should have been. So that way, okay, we can see there is some way to go, but it's not quite over double what they already have. It's like a sixth of what they already have, right? So that's the idea of the area principle. That is also being violated in this graph to the right, where you see the shrinking family doctor. If you actually look at these percentages, 1964, 27% of doctors were in family practice, whereby 1990, only 12% of doctors were in family practice. But if you look at these little dudes, our little scary doctor mans, this doctor man looks like a quarter of the size of this one, right? When if we actually dive into the numbers, that is, less than half, but this guy does not look less than half, because they're thinking of it just from head to toe when we're seeing the whole area of this creepy doctor graphic. So things to avoid, it would be, if you wanted to keep avoiding that area principal issues, look for truncating axes, which is what we see in the Fox News one. So anytime we cut off the axes, we don't have them go all the way down. And then like anytime we get too cutesy with the bars. So if we're not using actual bars and we're using something that has 2 dimensions and we're moving it so that we can see, like we're dragging that little cursor thing up into the right area, we're going to have this sort of issue where we're violating the area principle.